Oh, hey there. You again? Can't say I'm surprised that you're back for more. Well, we have a lot to cover today, so relax, grab a cup of joe, and don't operate any heavy machinery you would regret falling asleep at. So let's talk about the growth of functions. We say that the running time of a function is big O of f of n. We use big O for asymptotic upper bounds, since it bounds the growth of running time from above with large enough input sizes. It's the same as saying our function can't get, our function with respect to running time can't get any worse than this. So we say that the running time of some function f of x is less than or equal to c, which is a constant, times the running time of g of x, when x is greater than k. So k represents how much data we're inputting into our function before its pairing with c causes g of x to begin to grow more quickly than f of x. Let's give a specific running time to our functions. Let's say f of x is x squared plus x. In general, we could say that one of the upper bounds of our function is the most quickly growing component of that function. X squared is the most quickly growing component of x squared plus x. So g of x might just be x squared. Now we can see that x squared grows a little less quickly than x squared plus x because x squared plus x has that little plus x at the end there. However, when we multiply g of x times some constant c, then once k reaches, the input of our data reaches k or greater, then that function begins to grow as quickly or more quickly than our original function f of x. So then we could say that f of x is big O g of x. We could also say that x squared plus x is big O x cubed, because x cubed is far more quickly growing than x squared plus x, and so it might act as an upper bound. Or big O x factorial. However, we could not say that f of x that we've given here is big O of x, because no matter how much data we put into x, it will never grow more quickly than x squared plus x, even if we apply a very large constant c to it. Okay, so this first problem goes out to my 7 subscribers. Show that 2 to the power of n is big O 3 to the power of n, but big O 3 to the power of n is not big O 2 to the power of n. And I think we can begin with the first one. Show that 2 to the power of n is big O 3 to the power of n. And we can see that this holds true, right? 2 to the power of n is less than 3 to the power of n when n is greater than 0. So no matter what value we plug into n when n is 1 or greater, will cause 3 to the power of n will always grow more quickly and be a higher value than 2 to the power of n. So we say that our witnesses are c equal to 1 and k equal to 0, because 1 times 3 to the power of n will always be greater than 2 to the power of n, regardless of how large our input data is. Okay, so let's do the next part now. Is big O 3 to the power of n big O 2 to the power of n? Well, we have to show it's not. So let's suppose 3 to the power of n is less than some constant c times 2 to the power of n. We just do some algebra. We divide both sides by 2 to the power of n, and we get 3 over 2 to the power of n, which is less than constant c. But we can see that no matter what value we plug into n, right, since 3 over 2 is greater than 1, this is going to cause this expression to grow quickly and more quickly and more quickly. So we could graph it. Let's say that 3 over 2 to the power of n looks something like this. No matter what constant for c we choose, maybe c is right over here, f of x will always grow beyond the constant. So even if c were up here, the function will still continue to grow at some point and surpass the constant c. So since this is the case, we say that 3 over 2 to the power of n is unbounded. And therefore, three to the power of n is not big O, 2 to the power of n. Explain what it means for a function to be big O of 1. And simply put, this means it grows at the rate of a constant function. In other words, it doesn't grow. Execution does not depend on the size of the problem. So if we were to graph the running time, it would just be a flat line. No matter how large our data size became, running time would never increase of our function. Determine whether each of the functions 2 to the power of n plus 1 and 2 to the power of 2n is big O, 2 to the power of n. So let's begin with the first one. We need to try to get a 2 to the power of n isolated. And we can see this does grow more quickly than 2 to the power of n, and we can easily find 2 to the power of n within this function by using what we know of previous mathematics to bring this 1 in front of the 2 and multiply it by the base. So 2 to the power of n plus 1 is equal to 2 to the power of 2 to the power of n. This matches that same g of x times c notation we've seen before. So let's just say 2 to the power of n is our g of x, and 2 is our c. Well, this matches what we're looking for. So then all we need to say is that 2 to the power of n is big O to the power of n with c equal to 2, and input size data does not matter, so k is equal to 0. Remember, this 2 is coming from in front. We solved this expression and showed their equivalent. Okay, so this is our conclusion there. Let's go on to the next part of the problem. Is 2 to the power of 2n big O 2 to the power of n? Well, I don't think so. So let's suppose that 2 to the power of 2n is less than or equal to c times 2 to the power of n. However, we can see that this is already absurd, because if we do the algebra, we get 2 to the power of n, which is less than or equal to c, and 2 to the power of n can never, with a large enough input data size, could never be bounded by a constant c. So because 2 to the power of n is unbounded, therefore, 2 to the power of n is not big O 2 to the power of n. 2 to the power of 2n is not big O 2 to the power of n. Arrange by increasing big O. We're given a bunch of functions, and I think you should do this one on your own. So pause the video, determine on your own which ones are the slowest in running time and which ones are the most quickest in running time. And then when you're done, unpause the video, and I'll just have the solution available for you. Is this what you put? We can see that 1,000 times log of n is the most slowly growing of these functions, because log of n grows very slowly. Just because it's times 1,000 doesn't really mean anything, because as input data increases and increases and increases, the 1,000 becomes meaningless, and the growth rate remains log of n. Next is square root of n, then n times log of n. Then we have n squared over a million. Again, the a million doesn't matter for the same reason the 1,000 doesn't matter. The most quickly growing component is the n squared. Next, 2 to the power of n, 3 to the power of n, and 2 times n factorial. Anything factorial is basically the worst or terrible running time of a function, and if you ever wrote an algorithm which was n factorial, I'd probably fire you. All right, 3.2.61. Show that x cubed is big O x squared. So how do we do that? Well, we need to set up a limit. So recall back to calculus. I know it's been a very long time. And let's set the function we're trying to show is big O as the denominator and the big O as the numerator. So we say that the limit from x to infinity is x squared all over x cubed. From here, we just do some algebra. We get that the limit is 1 over x. Now, anything with 1 over, where x is approaching infinity, just becomes 0. So at the limit of this expression, we get 0. And when you've solved the limit and 0 is your answer, then you can say that x squared is big O of x cubed. Part 2, show that x log x is big O x squared. Well, let's set up a limit just like before. And then we can do some algebra, take x off the numerator and the denominator. And well, then we're kind of stuck. I'm not really sure how to evaluate it, but, well, look, an unknown benefactor left us a clue. Use L'Hopital's rule. Basically, that just means that when we can't evaluate this any further, we can take the derivative of the numerator and the derivative of the denominator to simplify our expression into some intermediate form and make it simpler to evaluate. So, what's the derivative of log of x? Well, it's just 1 over x. And the derivative of x is 1. And this expression is equivalent to saying the limit of 1 all over x. And this we know gets infinitely close to 0. So at its limit, our answer is 0, and therefore we say that x log x is in fact big O x squared. Show that x squared is big O to the power of x. We begin with our limit. All right. So from here, we have no choice but to use L'Hopital's rule. So we say this is equivalent to the limit as x approaches infinity of 2x all over the natural base, or the natural log of 2, times 2 to the power of x. But we're still stuck, so we use L'Hopital's rule again. This is equivalent to the limit going to infinity of 2 all over the natural log times the natural log, or just natural log of 2 squared, times 2 to the power of x. And from there, I think we're pretty much done, right? A constant divided by pretty much anything with a base to the power of x will get infinitely close to 0, so we say that our solution is 0, and therefore x squared is big O of 2 to the power of x. Show that x squared plus x plus 1 is not big O x squared. And intuitively you might be wondering, well, but it is big O x squared, right? The most quickly growing component of this function is the x squared component, so at a certain point, some constant times this function x squared would surpass x squared, or x squared plus x plus 1. And although that would be true, and it would be big O x squared, there's a little more truth to it. If we use the limit method, we can determine that it's not only big O, but it's a little something else as well. So we set up the limit here, already set it up. That's just equivalent to the limit, x goes to infinity, 1 plus x all over x squared plus 1 over x, right? Let's just combine this step with the next step. Divide 0 out, and we have 1 plus 1 over x plus 1 over x. If we evaluate this to, where x goes to infinity, that's just 1 plus 0 plus 0, or simply 1. So we're not getting 0 as output, because we've gotten a value out, which is a constant, like 1. We do not say we're big O. Instead, we say theta, or big theta. So x squared plus x plus 1 is big theta of x squared. And big theta is another way of analyzing the asymptotic bounds. While big O says our function can't get any worse than this with respect to running time, big theta says our function can't get any worse than this, but it also can't get any better than this. 3.2.75. For each of the following, determine whether f and g are asymptotic. Asymptotic just means, is g of x an upper bound, a lower bound, or a tight bound of f of x? So I've already set up our limit here. We can't do anything with it, so let's apply L'Hopital's rule to the numerator and the denominator. So take the derivatives. This is equal to the limit, x going to infinity, of 2x all over x squared plus 1 divided by 1 over x. The log of x squared plus 1 becomes this up here, and the log of x becomes 1 over x. From here, we just do some algebra. This 1 could multiply x squared plus 1. This x multiplies 2x, and we get the limit from x to infinity of 2x squared all over x squared plus 1. Again, we apply algebra. We divide 2x squared by x squared, and we divide 2x squared by 1. And we get the limit from x to infinity of 2 all over 1 plus 1 divided by x squared. Okay, now at this point we're done. 2 divided by 1 plus 1 over x squared is some constant divided by something that has an x squared in it. So this will tend to 0, and we get 2 divided by 1 plus 0 once we apply our limit. And now we're really done. This is just equal to 2. Because it's a constant which isn't 0, we say that f of x is big theta g of x. Is to say that f of x is tightly bound by g of x. We have 2 to the power of x plus 3, 2 to the power of x plus 7. We set up a limit, and we can take these values off of the power, bring them out in front, and multiply it by the base. So we get 2 times 2 times 2 times 2 to the power of x, and 2 times 2 up to 7 2's, which is just 128 times 2 to the power of x. We can also simplify the top. 2 times 2 times 2 is just 8. From there, it's easy. We take 2 to the power of x and 2 to the power of x on the numerator and the denominator. We cross them out. We're left with the limit from 8 all over 128. Because there's no x in there, that's just a constant, 8 over 128. Because we have a constant that's not 0, again we say f of x is big theta g of x. Okay, we have another two functions, 2 to the power of x and 2 to the power of x squared. So let's set up our limit. Okay, so we have a limit here. Where do we go from here? Well, we see that we have an exponent, so we can just subtract the superscript of the first exponent with the superscript of the second exponent because they share a base. So this is the same as saying we have the limit of 2 to the power of x minus x squared. And then we see that we have 2 to the power of something that grows to infinity. That's the same as saying that we have 2 to the power of infinity, and that's just infinity, right? So we don't have a constant that isn't 0, so it's not tightly bound. We don't have 0, so it's not big O, it's not an upper bound. What does infinity mean? Well, when we get infinity using the limit method, we instead say that f of x is big omega g of x. This is like the opposite of big O, right? So this is the lower bound. So what we're saying is that the running time of f of x cannot get better. That is, our execution time doesn't get faster than g of x. We're almost done. Let's keep trucking along. We have some function, we have another function, we set up a limit, and try this one yourself. So pause the video. If you don't want to wait, then I'll just give you the answer. Okay, so we see just like before, we have the same base. Well, we can subtract the superscript up here by the superscript down here. So that's the limit of x going to infinity of 2 to the power of x squared plus x plus 1 minus x squared minus 2x, which is just the same as 2 to the power of 1 minus x. So now as x tends toward infinity, we have 2 to the power of negative infinity, right? Because 1 minus x, or 1 minus infinity, is just really negative infinity. So the limit here gets down to 0. So we've gone full circle. We say again that f of x is big O of g of x. That g of x is an upper bound of f of x. Analyze worst time complexity. So I've written this algorithm here. Really nothing matters except for the loop. So at 5, step 5, and ending at step 20, we have a for loop. All of the steps between those two steps, from 6 to 19, have constant runtime, right? There's no nestled for loop. And because of that, we say that worst time complexity is just how many iterations we're doing here. So we have big O of n minus 1. It's n minus 1 rather than just n because we're going from 2 to n rather than from 1 to n. So the upper bound would be n minus 1. And again, these steps in between don't matter because they all have a constant runtime, so they don't contribute to our worst time complexity analysis. Last but certainly not least, we're asked again to analyze the worst time complexity of this other function, this algorithm. Again, nothing really matters except for the loop, right? So the loop begins at 3 and ends at 9. All of the steps between it, 4 through 8, can be done in constant time. So they do not add to the worst time complexity analysis, right? So we just say that because we're going through it, n number of iterations, I going from 2 up to and including n, we say that we have big O of n, and that's our worst time complexity. So just as kind of a side note, let's say somewhere in our function, maybe over here between steps 3 and 4, we had a for loop that goes from j, which begins at 0, to n. Well, then we have within a while loop, a for loop. So we have a loop within a loop. That's a nestled loop. The outer loop goes from n, and the inner loop, or n number of iterations, and the inner loop goes n number of iterations as well. So in other words, for every n iteration, we have n iterations. And if we did have another loop within the outer loop, our time complexity would be n squared. So we have to multiply the time complexity at times. We didn't have to for this example, but if there were a loop within a loop, then it would have been n squared. And like, comment, and subscribe if you want to see more wholesome content just like this.